today, ionization energy is our topic. We talked about this in Chem 1A a little bit. We're going to go a lot more in depth in AP Chem. But ionization energy is defined as the energy required to remove an electron from an atom or ion. So it takes energy to remove electrons because there's a force holding those electrons on the atom. And we know in physics, if you've ever had physics or if you've taken physics, that overcoming forces requires energy. And the best example I can give you is if a rocket wants to take off from Earth, that requires a large amount of energy because they're overcoming Earth's gravitational pull. The same idea applies to an electron being removed from an atom because it's trying to overcome that attraction from the nucleus. You have to overcome the attraction from the nucleus to pull the electron off. The same way that a rocket has to overcome Earth's gravitational pull to take off. It takes energy. And that energy is defined as ionization energy. So if we're looking at a metal that I supplied the ionization energy to, it becomes a positive ion and a free electron. It lost an electron, so now it has a positive charge. And then I can even take that positive ion, keep applying energy, supply more energy, and I get a metal with a 2+ charge and another free electron. This is called the first ionization energy. The energy required to remove the very first electron. One valence electron. This is the second ionization energy. And that's the energy required to remove a second valence electron. Or maybe now you've removed the only valence electron and you're removing it from a different different energy level. We're going to find out later that this ionization energy is higher than this ionization energy. And we'll talk about why. But you could continue removing electrons, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, whatever ionization energies until you have no electrons left. And all you have is a nucleus. It's going to take a huge amount of energy, but it can be done. Questions so far? Okay. Let's talk about factors that affect ionization energy. So if I'm trying to remove an electron from an atom, any atom, there are two kind of three things that I have to worry about, or things that are going to affect how much energy it takes to remove that electron. The first one is the distance from the nucleus. That has the largest effect on ionization energy. The farther an electron is from the nucleus, the easier it is to take away. The less energy is required. So, larger distance lower ionization energy. This has the biggest effect on ionization energy. The farther the electron that you're trying to remove is from the nucleus, the lower amount of energy it takes. Less energy. The second thing that has an effect on it is the size of the nucleus. The more positive the nucleus is, the harder it is to pull an electron away from it. Bigger nuclei lead to higher ionization energies if the distance is equal. Distance is more important than the nuclear size, though, when we're talking about ionization energy. And this is all because of Coulomb's law. The force on the electron is equal to a constant. The charge of the electron, the charge of the nucleus, over the distance between them squared. Coulomb's law is one of the most important things in AP chemistry. We will talk about Coulomb's law over and over and over again. If you draw a complete blank on the AP test, use Coulomb's law. 5 times out of 7, you'll get it right. Coulomb's law is so important because chemistry is all about electrostatic attraction. A proton attracted to an electron and some distance between them. So, larger distance, smaller force, therefore less energy. And distance matters more because it's squared. It's squared on purpose because it's very, very important. It has a great effect on the force. Then we have the size of the charges. The charge on an electron is constant. That's not changing. We're always going to have an electron. It's this nuclear size that's changing. It's not squared, so it doesn't have as big of an effect as distance, but it still does affect the force. Bigger nucleus, bigger force, more energy. The third one that isn't in Coulomb's law and only makes slight differences in ionization energy is electron repulsion. We know that electrons repel each other because they have the same charge. So if we're in an energy level, or even a sub-level, and those electrons are repelling, more electron repulsion is going to lead to lower ionization energies. When the electrons are repelling, it's easier to take an electron away. So more electron repulsion leads to lower ionization energy. This is a tertiary factor. We look at distance first, then we look at the size of the nucleus. If those two things are the same, and we're trying to compare things, then we would look at electron repulsion. This is the most important thing to look at. Then the size of the nucleus. Then you look and see if there's electron repulsion. It has a slight effect that you're going to see in just a second. Questions so far? Okay, we're going to look at some trends in ionization energy. Okay, so this graph is a graph of the ionization energies in kilojoules per mole of the first 20 elements. So we can look at the trends that happen on the periodic table as we go across rows and down columns. So we have the first one, hydrogen. Hydrogen has a middle moderate ionization energy. One single proton holding on to one single electron that's very close to it. So I'm going to keep referring to this. Distance is really small. Charge to charge ratio is a 1. So you wind up with a moderate force and a moderate ionization energy. Right in the middle. Then we move to helium. Helium has the highest ionization energy because the distance is very small, only one energy level, but the nucleus to electron ratio, the proton to electron ratio is 2 to 1. That's a big ratio. So we have a huge force and a very high ionization energy. Removing an electron from helium is extremely difficult. You do not find ionized helium very often. Okay, and then we drop way down here to lithium. Why this big drop? What happened from helium to lithium? You gained an energy level. You went from 1 energy level to 2 energy levels. My distance increased a lot, so my force decreased a lot, and now I have a low ionization energy. So right now, we have our nucleus. We had hydrogen in the middle. Helium was very high. Now we're at lithium. And then it goes up a little bit from lithium to beryllium. Why did it go up? What changed? I added an electron, but what else did I add? I added another proton. So now my positive pulling on my electron is more. So my force is greater. But then I get this drop. I've added a proton, but now my ionization energy is lower. So beryllium, boron. What happened? We have hydrogen, helium, lithium, beryllium. Now boron. What do we know about this P sublevel? Is it just a little bit farther from the nucleus than the S? Yes. So from beryllium to boron, I added a new sublevel that's just slightly farther from the nucleus. So the ionization energy is slightly lower. I increased my distance just a little bit. Then I go up because I added a proton, but no new sublevel or energy level. I go up again because I added a proton, but no new energy level or sublevel. And then I get a drop again. Why? I didn't add anything. I didn't add an energy level. I didn't add a sublevel. I added a proton. Now I have electron repulsion coming into play. These 4 electrons in this P sublevel are repelling enough that it decreases my ionization energy a little bit. And then I add another proton and an electron. I add another proton. Now I'm at neon. It's a noble gas. It has a high ionization energy. And then I plummet again. Because I added another energy level. So now we're at sodium, magnesium. Then I add a P sublevel. P1, P2, P3. A tiny little drop because I get electron repulsion. P4, P5, P6. This is a noble gas. And then I plummet all the way down to potassium. It has the lowest ionization energy of all of these because I added another energy level. And then I go up just a little bit for calcium. Do you see how all of this goes together? Distance matters the most, then nuclear size, and then sometimes we get these weird things that happen because of electron repulsion. So in Chem 1A, I was happy if you understood how nuclear size and distance mattered. Now they're going to ask you questions about electron repulsion as well. These anomalies that don't follow the pattern. Okay, in general, as we go left to right on the periodic table, what happens to ionization energy? Left to right, what happens in general? It increases overall. Because as we go left to right, we're adding more protons to the nucleus. There are places where it dips, but the general trend is an increase in ionization energy. As we go from top to bottom, ionization energy. So from top to bottom, helium, neon, argon, ionization energy decreases because I'm adding more energy levels. On my test or their test, you're going to have to explain why adding more energy levels decreases ionization energy. And it all goes back to Coulomb's law. Adding more energy levels increases distance. Increasing distance decreases force. Decreasing force decreases energy. It's that critical thinking that is important on this test. They don't care if you can memorize that it decreases as you go down. Fifth graders can memorize that, right? You have to understand why. Questions? Okay, let me erase. All right, you may also see something like this. These are successive ionization energies for sodium. And on the test, they're not going to tell you which element it is. They're going to have you figure out which element it could be or what group it could be in. But if we look at these ionization energies, we have 496 is my first ionization energy. My second one is 4562. 6912, 9543, 13353, 16610, 2114, 25, 29, 141,000, 159,000. This is the energy required to remove the first electron, the second, the third, the fourth, the fifth, the sixth, so on and so forth. So you can look at this and you can determine how many valence electrons does this atom have. How many? One. It has one because from the first removing one electron to removing the second electron, that energy jump is huge. Removing the first one only takes 496 kilojoules per mole. Removing the second one is 10 times more energy, 4,500. And then all of these are fairly close, no big jumps. We do see a big jump. We remove 1, 2, 3, 4, 5, 6, and then we see a little bit of a jump here because we go from P to S within that energy level. But then we see another big jump here as we go from second to third energy level. The inner energy level, second energy level, third energy level. If we look at sodium, plus 11, 2, 8, and then 1. Removing the first one takes 496 kilojoules per mole. Not very much. Then removing these 6 are these right here. Then these 2 here. And then those inner ones very high amounts of energy, hundreds of thousands of kilojoules per mole. Removing inner energy level electrons takes so much energy because they're so close to a big nucleus. You're going to see tables like this, and they're going to ask you how many valence electrons does this atom have. You're going to look for these big jumps. See where the big jumps are? You'll figure out how many energy levels does it have. How many does it have in its outermost energy level? And then later we can use that to determine what's its most common charge. What ion is it? 1 plus, 2 plus, 3 plus. All right.